Questions? Okay, questions about this part. Now what we have done. Now we had this metal, conductor, arbitrary shape. Then we were asking this question. Now, first we had, in the previous slide, we had said that if we have a conductor, since inside the conductor we cannot have any electric field, any charge we put inside the conductor cannot stay there. It has to move outside or on the surface. But then there was this question. What happens if we make a hole, a cavity inside the conductor and put the charge over there? Then what happens? It cannot move anywhere. That charge will stay there. So we have this hole inside the conductor. And in it, we placed our charges. Now here, still the electric field is 0 because it's inside the conductor. Now this region is not a conductor, so we can have a non-zero electric field in this region, but not here. Then again we chose a Gauss surface inside the conductor. Now again, I mean, when you think of this Gauss law is valid for any surface that you can imagine. We just pick up surfaces that will be useful for us. So in this case, such a surface, such that it will be useful, I mean, the property of this surface is it is always inside the conductor. And for this surface, if we apply the Gauss law, we said that Q dot ds is equal to E dot ds is equal to 0. But Gauss law tells us that E dot ds around any closed surface should be the total enclosed charge divided by the epsilon 0. This Q enclosed is the total charge inside my surface. Not necessarily only the ones that I have, but also the ones that move inside my surface after I put the charge. Well, I already have a positive charge at this point inside my surface. Since the total enclosed charge, the total enclosed charge will be the charge that I placed there plus any other charge that is positive charge induced. Now, how will it induce? Well, I have this positive charge over here. It will attract the electrons inside the conductor, so electrons will accumulate on the inner surface of this conductor. So, since there are excess electrons on the inner surface, there will be a negative charge on the inner surface. And the total charge in the inner surface is what I call this induced charge. The charge that moved inside this surface due to the presence of this charge that I put over there. And from here we can conclude that the total charge induced is nothing but minus Q. So that if I put a positive charge plus Q in this cavity, a net charge minus Q accumulates on this inner surface, so that the total charge here will be 0. And of course, since minus Q had moved inside this cavity, a plus Q should be somewhere else because my conductor was neutral to start with. We all know that it cannot be inside this conductor. It cannot be in the inner surface. So the only place that it can be is on the outer surface. So I should have some positive charge outside my metal. Because the total charge of my conductor will be Q induced plus Q outside. And this is 0 to start with. So what happens to the electric field lines that start from this positive charge? They don't pass through the conductor. They start from the positive charge and they terminate at the negative charges on the inner surface. And then I have positive charges outside. So from those positive charges, I have new electric field lines emerging. Okay, good question. So your friend is asking this one. We have this conductor. We imagine some inner surface. We put some positive charge inside. So your friend is asking, what happens if we take such a Gauss surface? Well, E dot ds will be equal to Q over epsilon 0. Because the net charge inside my surface is Q. The electric field on this Gauss surface need not be 0, so E is not 0. And this relation, in fact, tells me that it is definitely not 0. There is an electric field outside created due to this positive charge. So let's see. The total charge of the conductor, let's say it is equal to Q1. This is the total. I already charged my conductor by some means. I just give some charge. There is a cavity inside my conductor. And in this cavity, I put a charge small q. Now the question is, what is the charge in the inner surface? What is the charge in the outer surface? Why? Well, there are infinitely many choices for that. This one, here. Plus Q and 0, this is one choice. Q1 over 2, Q1 over 2, this was another answer. Why? You see, I mean, whether you can guess the right answer or not is of secondary importance. The most important thing is how do you get that answer? So negative charges, so you are not meaning plus Q in the inner surface. No, I'm not saying that the conductor is neutral. The conductor has charge Q1. Let's call this small q1, small q2. Again, we have the Gauss law. If I imagine such a Gauss surface, E dot ds for this Gauss surface will still be 0. because my surface is inside my conductor, and inside the conductor we cannot have electric field. Inside the conductor, electric field is 0, so this integral is 0. That means the total charge inside this Gauss surface have to be 0. Well, what are the charges? I have this plus charge, plus Q is inside my conductor. And there is also the charge in the inner surface of the matter is inside my Gauss surface, sorry. So Q is in my Gauss surface, Q1 is in my Gauss surface. So the total enclosed charge in my Gauss surface is nothing but their sum, which should be 0. So it tells me that the charge in the inner surface have to be equal to minus Q, so that it will cancel this plus Q. But we also know that the conductor has a total charge Q1. Minus Q is on the inner surface. The rest has to be on the outer surface. It cannot be inside. It cannot be in the inner surface because the charge in the inner surface is minus Q only. So this much is in the outer surface. No. I'm taking an imaginary surface, that's true, but I'm giving a restriction on it. It has to remain inside my metal. Only if it remains inside my metal, I can say that E is 0. That's not? I didn't understand. Yeah, that is my inner surface. Yeah. No, I'm including the inner surface. I can include anything I like. It's not a circle, by the way. It's a surface. It's a closed surface. Just think of it as a three-dimensional image. This is just a two-dimensional cross-section of that three-dimensional image. This is a closed surface. I can pick up any closed surface that I like. You are completely free to choose your surface, this Gauss surface. And for this example, I'm choosing a Gauss surface that lies within my conductor everywhere. Tell me one. No, tell me one. You mean this inner surface? Okay, so let's do. E dot ds will not be equal to 0, and this will be equal to Q over epsilon 0. End of the story. Nothing more I can do. I mean, we didn't create it. You see, Gauss law is valid for any surface. For this surface also, well, this tells me that in fact the electric field inside this cavity cannot be 0. It has to be finite. That's the only conclusion I can derive from here. I choose another Gauss surface. This time it lies inside the conductor. And from this Gauss surface, I can derive this conclusion. I choose a third Gauss surface. Let's choose, I can choose this Gauss surface, for example. For this one, E dot ds will be equal to Q plus Q1 over epsilon 0. You choose one Gauss surface. You evaluate E dot ds for that Gauss surface. You calculate the total charge enclosed for the same Gauss surface, and they are related. That's what Gauss law tells me. Which Gauss surface should you use? Whichever one you like. Whichever one serves your purpose. Gauss law is valid for any surface. Where? Okay. Well, well, I mean, you can choose any Gauss surface you like, so don't choose a Gauss surface that will make your life hard. I mean, you just divide it into two. You just assume half of them is inside, half of them is outside. That gives you the correct answers, but as I said, you are free to choose any Gauss surface that you like, but don't use that freedom to choose the most complicated Gauss surface. Okay, now we have this infinite line. Lambda is the charge per unit length. What is the electric field? You mean the point charge? No, in this example. This one. In the inner surface, we have a total charge minus Q. In the outer surface, we have a total charge Q1 plus Q. This is the charge in the outer surface here. The charge in a conductor cannot be inside the conductor. It has to be on the surface of the conductor, either the inner surface or the outer surface. Well, we will study the so-called dielectrics, which will be insulators. In that case, we will have some charge accumulation in the inner surface, not this much. Some charge accumulation on the outer surface, again, not this much. And we will have electric field lines going through the insulator. We will study them, don't worry. But just not yet. Questions? Now, how can we calculate the electric field here? Yes. There's a lambda units of charge per unit length. If let's say lambda is 1 coulomb per meter, in 1 meter you have 1 coulomb of charge uniformly distributed. Well, of course, you can calculate this using integrals, which you will do in the homework. Now, in this one, let's try to use the Gauss law. Now, how can we use the Gauss law? How? Why? For the cylinder, we also have to use double integrals if you are trying to evaluate. If you will be evaluating the integrals. You are changing the electric field. We want to find the electric field of this case. How do we choose a Gauss surface? Okay. Okay, you convince you about my cylinder. Let us choose this cylinder. Do you agree? This will not work. It should be in the center. Now, first before trying to find a Gauss surface, you should first think about what does the electric field look like? Okay, we will not evaluate the electric field, but what does it look like? What are its symmetries? If you remember our previous case when we were looking at the point charge, now we first concluded that the magnitude of the electric field on this cylinder is the same, on this sphere was the same everywhere. And in fact, that observation led us to choose such a spherical Gauss surface. So we should first look at the electric field. How does it look like? That will let us determine what kind of a shape we should choose. So what will the electric field of this infinite line look like? Your friend is saying that we will have one field line that moves in this direction. Okay. So your friend is basically saying that the electric field lines will go straight out away from the line. Do you agree? Why? Okay. You see, this is also out. Why? I mean, without looking at the integrals, your friend is basically saying that if you look at this point, this part will create an electric field. There is a symmetric part on the other side. It will also create an electric field. This will create an electric field in this direction. The other one will create an electric field in this direction of equal magnitudes. One of them will be pointing like this, the other one is pointing like this. So when you sum them up, you will get an electric field pointing in this direction, perpendicular. Well, that's a reasonable, an acceptable explanation. Okay, they will definitely look outside. What next? These are our electric field lines. Let's also look at it from the top. And if you just this is our line of charge. Let's just rotate it. So this is our line of charge lying over here. And if you look at from the top, you will see that the electric field lines are just like this. Now, two questions. Let's take 2 points at the same distance from our charge distribution. This point A, point B. What can you say about the magnitudes of the electric fields? They should be the same. Why? That's the same distance. Or put in other words, we can say that we have translational symmetry. If you take your system, translate it along your line, nothing changes, it just looks the same. If you translate point A to the point B, nothing should change. So the electric field at the point A has the same magnitude as the electric field at the point B. They even have the same direction. Now let's think that this is the point A, and we just imagine this point C over here. What can you say about the electric field at the point A and electric point at the C? Their magnitudes. Again, they have the same magnitude, because if you just rotate this charge distribution, again, nothing changes. So if you rotate your system around this line, point A just becomes point C. So nothing should change. That again tells me that their magnitudes have to be the same. So this basically tells me that if I just consider all the points that are at the same distance from the center, from my line of charge, they have the same magnitude of the electric field. Furthermore, they are radially outward. This guides me to choose a Gauss surface that's a cylinder, because all the points that are equidistant from a given line they form a cylinder. So that's why we are choosing a cylinder. Cylinder whose center is our line of charge, not any cylinder. So that's why if we, okay, this is our line of charge. If you choose a cylinder like this, it doesn't work, it won't work. Because the electric field at different points on the cylinder will have a different magnitude. But if we choose a cylinder whose axis coincides with our line of charge, now all the points on the side of the cylinder is at the same distance from my charge distribution, and hence on every point on the side of my cylinder I have the same electric field. There's of course one subtle point. Now let's look at the Gauss law. E dot ds. Now this is the integral of the electric field over a closed surface, not any surface, a closed one. Just the size of the cylinder doesn't form a closed surface. This closed surface will be E dot ds on the sides plus E dot ds on the top plus E dot ds on the bottom of the cylinder. Now this is what we want. But these two, we don't want them. Because on the top, the magnitude of the electric field changes all the time. On the bottom, the magnitude of the electric field changes depending on which point you are on the bottom. So what will we do with these? Fine, but I want to relate that total to the electric field. And here, in this one, I know the magnitude is constant, so the magnitude I can just take it out. But these ones, the magnitude is not constant. I cannot take it out, so it will not allow me to solve for the unknown magnitude of the electric field on the sides. So you can just think of this, I'm trying to reduce my unknowns. I know the Q, the charge over epsilon 0. That is known. I'm trying to relate that known to one other unknown, the magnitude of the electric field on the sides. But I don't know these things also. So I have one equation, but it involves many unknowns. Yes. Why? True. You see, if you look at the top, how do we define ds? You just take an area, and ds is the perpendicular to that area. But that is perpendicular to the electric field at that point. Similarly, if you look at the bottom, you take this area, ds, this is the bottom. This is also perpendicular to the electric field at the bottom. Because we had already seen here that the electric field is pointing away from my charge. So if this is your line charge, the electric fields are pointing in this direction. But at the top of my cylinder, this is my area vector. This is my electric field vector. They are perpendicular. Cosine of 90 is 0. In the bottom, this is ds. This is still my electric field. the electric field is horizontal to the surface, which means it's perpendicular to the surface vector. Again, the angle between the surface vector, ds vector, and my electric field is 90 degrees, so it is 0. It just basically means that E dot ds at the top is equal to E dot ds at the bottom, and they are both equal to 0. This is 0. This is 0. But of course, this also tells me that I have to choose a right cylinder. I cannot choose a cylinder whose top and bottom parts are tilted, for example. You have to choose a cylinder in which the top and the bottom are perpendicular to the S vectors of the top and the bottom are in the direction of your line charge. Now this was our problem. We have our cylinder. If we looked at it from the top, these were our electric field lines, and this is my cylinder. Let's say we have radius small r, and let me call this vector perpendicular to the surface at everywhere rho hat. It is pointing like this here. It is pointing like this here in this direction over there. It's the unit vector perpendicular to the surface. We already said that the electric field, okay, it only depends on the distance from the cylinder center from the charge line charge distribution. So its magnitude depends only on r. And furthermore, we already said that it is just pointing away from my line charge. ds is again its magnitude. It's again in the rho hat direction. I will just assume that my cylinder has a height L. And L will not be important. You can just choose it, anything you like. E dot ds is equal to the ds E. Since there are two vectors in the same direction, E and ds, the scalar product is nothing but the product of their magnitudes. The angle between these two vectors is 0. Now E dot ds on the sides will be equal to ER times ds. Again, I'm just integrating over the sides of my cylinder. Side of my cylinder. But this just means I'm just dividing the side of my cylinder into very small bits. I'm just summing them up. But we already said that the magnitude of the electric field is the same at every point on the side. So this ER is just a constant in this integral. What is the ds integral? The result? 2 pi r times L. This is E times R times 2 pi L. 2 pi r times L. Now we can use the Gauss law, finally. We first studied the electric field. We found that it has the same magnitude on the side of a cylinder. So we just assume the Gauss surface, which has the shape of the cylinder. And then we evaluated E dot ds on this cylinder. And we found that E dot ds on this cylinder is nothing but the magnitude of the electric field at a distance r from the charge distribution times 2 pi r times L. This is what we obtain. Of course, this integral, we already said that it might receive contribution from the side and from the top and from the bottom. But we had already said that from the top and from the bottom, it doesn't receive any contribution, because on the top and on the bottom, ds and E vectors are perpendicular to each other. So there's no contribution from the top, no contribution from the bottom, only contribution is from the side, and the contribution from the side has this expression. Now we have the Gauss law. What is the charge inside this cylinder? Lambda times, remember lambda is the charge per unit length. Lambda times L is the total charge, because lambda is the charge per unit length. The total length of the wire inside my cylinder is L, so the total charge is lambda times L. Lambda times L over epsilon 0. So L's, they just cancel. And the electric field, it just turns out to be 1 over 2 pi epsilon 0 lambda over r. This is the magnitude. The electric field itself is 1 over 2 pi epsilon 0 lambda over r in the rho hat direction. This is the electric field vector. Questions? I will give you the Gauss law. And if you will need to use this formula, I will ask you to derive it, don't worry. I mean, you will do it, don't worry. I mean, you can just divide it into very small segments, calculate the contribution of the electric field of each one of these segments at this point, and integrate them over. You will get the same result. A and C, they are at the same distance from the center. They are at the same distance. Only in that case they have the electric field at those 2 points have the same magnitude. Any other questions? Okay, see you on Tuesday.